21 new nuclear reactors are expected to be set up by 2031. Department of Atomic Energy. Well, this is something very interesting. India will now be able to generate more energy in an eco-friendly manner. Hello all, welcome to the course on nuclear power plant. Let's get started and understand how electricity is generated in a nuclear power plant. By the end of this module, you will be able to explain the working of a nuclear power plant, describe the components of nuclear power plant, describe the working of different nuclear power reactors, identify the factors affecting location of nuclear power plant, list few nuclear power plants of India. A generating station in which nuclear energy is converted into electrical energy is known as a nuclear power station. In nuclear power station, heavy elements such as uranium U-235 or thorium TH-232 are subjected to nuclear fission in a special apparatus known as a reactor. The heat energy thus released is utilized in raising steam at high temperature and pressure. The steam runs the steam turbine, which converts steam energy into mechanical energy. The turbine drives the alternator, which converts mechanical energy into electrical energy. Every source of energy comes with its own set of advantages and disadvantages. Let's see what they are for the nuclear energy. Click each cooling tower to learn more. The schematic arrangement of a nuclear power station is shown in the figure. The whole arrangement can be divided into the following main stages: nuclear reactor, heat exchanger, steam turbine, alternator. Let's get started and understand the components in detail. First comes the nuclear reactor. It is an apparatus in which nuclear fuel U-235 is subjected to nuclear fission. It controls the chain reaction that starts once the fission is done. The components of a nuclear reactor are fuel, control rods, moderator, coolant, shield and containment, steam generator, pressure vessel or pressure tubes. Click each component to learn more. The coolant gives up heat to the heat exchanger, which is utilized in raising the steam. After giving up heat, the coolant is again fed to the reactor. The steam produced in the heat exchanger is led to the steam turbine through a valve. After doing a useful work in the turbine, the steam is exhausted to condenser. The condenser condenses the steam, which is fed to the heat exchanger through feed water pump. The steam turbine drives the alternator, which converts mechanical energy into electrical energy. The output from the alternator is delivered to the bus bars through transformers, circuit breakers and isolators. Material in the core which slows down the neutrons released from fission so that they cause more fission. It is usually water, but may be heavy water or graphite. The ideal moderator has to be light or atomic mass comparable to neutron mass for efficient slowing down. Not neutron thirsty, that is, does not capture neutrons. Cheap, not inflammable. Control rods are the most important part of a nuclear reactor in nuclear power plant and are made up of barium or cadmium. It controls the ongoing nuclear reaction by absorbing the neutrons, and we can also control the energy production as per the requirement by inserting the control rods accordingly. Control rod materials, selection criteria, neutron absorption cross-section, adequate mechanical strength, corrosion resistance, chemical and dimensional stability, relatively low mass to allow rapid movement, fabricability, availability, and reasonable cost. The source of the reactor is intense radioactivity. The released radiations are very dangerous. So, for that situation, shielding is providing a grip to the radioactive rays. To prevent the radiation, thick concrete shielding along with the pressure vessel is provided and the radiation is escaped into the atmosphere. To develop nuclear energy, the nuclear fuel material are burnt by the nuclear fission. The nuclear fuel can be referred as a fuel. The physical objects should be composed with fuel material and mixed up with the structural neutron reflecting materials or neutron moderating materials. In many cases, the nuclear fuel contains the heavy fissile elements which are capable for the nuclear fission. The fuels are hit by the neutrons. At that case, they have the capability of emitting neutrons when they are broken separately. So, from that, there is a possibility of self-sustaining chain reaction, which releases the energy and controls the rate of nuclear reactor. Otherwise, a rapid uncontrolled process can be observed in the nuclear weapons. Most commonly used nuclear fuels are uranium-235 and plutonium-239. The movements of refining, mining, purifying, disposing of nuclear fuel together create the nuclear fuel cycle. By using some other types like and some more elements produce the small amount of nuclear power by using the radioactive decay in the generators and in other cases of atomic batteries. In nuclear fusion, tritium can be used as fuel. Important properties of fuel materials: thermal conductivity, thermal expansion, melting temperature or solidus temperature, compatibility with clad, coolant, mechanical properties such as hardness, creep, etc. There are various types of nuclear reactors. They are pressurized water reactor or PWR, boiling water reactor or BWR, CANDU, pressurized heavy water reactor or PHWR, advanced gas cooled reactor or AGR, light water graphite moderated reactor or RBMK, fast breeder reactor FBR, fast neutron reactor. Click each colored tab to learn more. This is the most common type with over 280 operable reactors for power generation and several hundred more employed for naval propulsion. The design of PWRs originated as a submarine power plant. PWRs use ordinary water as both coolant and moderator. The design is distinguished by having a primary cooling circuit which flows through the core of the reactor under very high pressure, and a secondary circuit in which steam is generated to drive the turbine. A PWR has fuel assemblies of 200 to 300 rods each, arranged vertically in the core, and a large reactor would have about 150 to 250 fuel assemblies with 80 to 100 tons of uranium. Water in the reactor core reaches about 325 degrees Celsius. Hence, it must be kept under about 150 times atmospheric pressure to prevent it from boiling. Pressure is maintained by steam in a pressurizer. In the primary cooling circuit, the water is also the moderator, and if any of it turned to steam, the fission reaction would slow down. This negative feedback effect is one of the safety features of the type. The secondary circuit is under less pressure and the water here boils in the heat exchangers, which are thus steam generators. The steam drives the turbine to produce electricity and is then condensed and returned to the heat exchangers in contact with the primary circuit. This design has many similarities to the PWR, except that there is only a single circuit in which the water is at low pressure, or about 75 times atmospheric pressure, so that it boils in the core at about 285 degrees Celsius. The reactor is designed to operate with 12 to 15% of the water in the top part of the core as steam, and hence with less moderating effect and thus efficiency there. BWR units can operate in load following mode more readily than PWRs. The steam passes through dryer plates, steam separators above the core, and then directly to the turbines, which are thus part of the reactor circuit. Since the water around the core of a reactor is always contaminated with traces of radionuclides, it means that the turbine must be shielded and radiological protection provided during maintenance. Cost of this tends to balance the savings due to the simpler design. Most of the radioactivity in the water is very short-lived, so the turbine hull can be entered soon after the reactor is shut down. A BWR fuel assembly comprises 90 to 100 fuel rods, and there are up to 750 assemblies in a reactor core, holding up to 140 tons of uranium. The secondary control system involves restricting water flow through the core so that more steam in the top part reduces moderation. The 4 factors affecting the location have been mentioned on the screen. Click each map pointer to learn more. Availability of water. As sufficient water is required for cooling purposes, therefore the plant site should be located where ample quantity of water is available. Example, across a river or by seaside. Distance from populated areas. The site selected for a nuclear power station should be quite away from the populated areas, as there is a danger of presence of radioactivity in the atmosphere near the plant. However, as a precautionary measure, a dome is used in the plant which does not allow the radioactivity to spread by wind or underground waterways. Disposal of waste. The waste produced by fission in a nuclear power station is generally radioactive, which must be disposed of properly to avoid health hazards. The waste should either be buried in a deep trench or disposed of in sea quite away from the seashore. Therefore, the site selected for such a plant should have adequate arrangement for the disposal of radioactive waste. Transportation facilities. The site selected for a nuclear power station should have adequate facilities in order to transport the heavy equipment during erection and to facilitate the movement of the workers employed in the plant. Here is the list of nuclear power stations in India. The table on screen depicts the power station, its operators, the state which it lies in, the types of nuclear reactor, and the total capacity of the electricity generated in the power plant. We now have come to the end of this module. Here is a quick recap. We have learned that a generating station in which nuclear energy is converted into electrical energy is known as a nuclear power station. The whole arrangement of nuclear power plant can be divided into the following main stages: nuclear reactor, heat exchanger, steam turbine, alternator. There are various types of nuclear reactors. They are pressurized water reactor or PWR, boiling water reactor or BWR, CANDU, pressurized heavy water reactor or PHWR, advanced gas cooled reactor or AGR, light water graphite moderated reactor or RBMK, fast neutron reactor, breeder reactor.